right, good afternoon. Good afternoon, everyone. Welcome. It's really energizing to see all of you, beautiful faces out here. I mean, it's been 2 years since we've held this event, View from the Top, which is designed to bring leaders from industry, business, and the arts to come to share their perspectives, their experience, and their wisdom with us in the Berkeley engineering community. I'm Sujay King Liu. My preferred pronouns are she, her, and hers, and I'm Dean of the College of Engineering here at UC Berkeley. So it's my pleasure to host this event, but before going any further, I'd like to acknowledge and express appreciation to our co-hosts of this event, the Society of Women Engineers, the student group. Let's give them a shout out. I'd also like to extend a special welcome to members of our Dean's Society for joining us here today. So as I mentioned, this series was on hiatus for a couple of years, and I'm super excited that the person to come kick off this series in person again this year is Dr. Ann Kelleher. She is a leading executive in the semiconductor industry. She is she's the Executive Vice President and General Manager of Technology Development for Intel, which is the leading semiconductor chip manufacturer in the world. You might know that semiconductor chips are the electronic brains of all the modern electronic devices that we depend on to live, work, and play. So it's really amazing that Intel allowed Ann to come join us today, share with us her wisdom. Now, before she was in charge of technology development at Intel, she actually managed all of Intel's manufacturing operations worldwide. And that includes not only running the factories, but designing and building them and managing the supply chain. So it's a huge job for Dr. Kelleher. So it's really impressive. Now, in her current role, she's in charge of research and development for future generations of chips that are going to transform the way that we live, work, and play. So she'll talk a little bit about that. I want to give her time to talk, but I just want to say that she earned her degrees, all 3 degrees in bachelor's, master's, and PhD degree in electrical engineering from the University of College Cork, UCC, and it's one of the most prestigious universities in Ireland. And she just told me today that she was the very first female to earn a PhD in electrical engineering from that university, and it was not that long ago. It was in the 90s. So time is changing, and technology is transforming the world, and hopefully for the better. So please join me in welcoming Ann Kelleher to the stage to give us a presentation. I forgot to mention that we have people who are viewing outside as well, but there is lunch going to be provided to all of you who are here at the end of today's event. They'll be outside in the atrium, so the box lunch is for everybody. There should be enough for everyone after the event today. So Dr. Kelleher will first give a short presentation, and then she and I will have a fireside chat, and we'll open it up to questions from all of you. All right, thank you.
Thank you, Dean Liu. And it's my pleasure to be here. First of all, I want to check, can you all hear me? At the back, great. All right, so my last time on this campus and my first time on this campus was in 1992, so it's a pleasure to be back. I visited you when I was doing my PhD. It was an informal visit. I came to visit another PhD student here who was from my university in Ireland, so it's a pleasure to be back. And it has changed a little since 1992. And so I'm very happy to see that. One other thing I'll say, maybe Dean Liu took me back to my college days. I'll just go a little bit further back. I grew up in a very small, I would say village, town, well, I won't call it town, right, in the southwest of Ireland. It was in Cork. I grew up, my parents were farmers. So I started from working to basically living and growing up on a farm to the local town, basically the local school. There was 12 in my class in I guess you call junior or junior high here. I'd call it primary school. And then I went on to the local town where I went to school with, there were nuns at the time who ran the local school. They were all in their 80s and 90s. Now, since then, the school has closed from being run by a convent and nuns, is now run by the public education system. So at that point in time, when I was going to school at the high school level at that time, the typical roles for females were you were going to become a teacher, you were going to become a nurse, or you went to the bank. I said I wanted to, first of all, I said I wanted to be a vet, right? And my mother didn't really like that because I grew up being in the farm. She came up with all the list of infectious diseases a human could get from animals. So we continued in that battle, and she decided I would be a doctor. So I said, you won the first battle, I'm going to win the second one. So then I went and I started looking up what else I liked, and maths and science and engineering was really what caught my attention, and I started studying electrical engineering degree in University College Cork. Now you have the rest. So I'm going to talk a little bit around some of this is the history. This is University College Cork. The story about University College Cork, it was built in the time in Victorian era of the United Kingdom. They decided they were going to fund 2 universities in Ireland, one in Belfast and one in Cork. They mixed up the drawings, and the drawings for the Cork one went to Belfast, and the Belfast one went to Cork. We won. Bottom line is we got the nicer building. So this is University College Cork. I studied there. I started in basically 83 to 87 is when I did my undergraduate, then I did master's, and then I did PhD. And as part of my PhD, I did part of it in Cork, but many of you are familiar with IMEC in Belgium. I did part of my PhD in IMEC in Belgium. My PhD was funded by the European Space Agency, so it gave me a very good opportunity to work with the European Space Agency in Noorwijk in Holland, as well as spending time in IMEC. So I remember this period of I would say, my formative years with very, very great fondness. And believe it or not, there is stuff that I learned back at this period of time which are really foundational for the work that I do today. So as you're going through your student days, and there may be some stuff that you're learning that you're scratching your head and saying, why am I doing this? Why am I learning this? Will I ever use it again? You never know. It will be useful at some point within your career. And I found that a lot of what I learned in the fundamentals in semiconductors at that period of time is absolutely essential for the job I'm doing in leading technology development today. So, Sujay gave a little bit to say semiconductors, that it's the brains of many of the electronics. So I think 3 years ago, if many people didn't know what semiconductors were pre-COVID, I think after COVID and after the impact of supply chain shortages or shortage in semiconductors, I think most people in the world today know what the role of semiconductors, or at least appreciate the impact of semiconductors within the world and how we operate today. Before, I would get asked questions of what do you do, and you try and explain, and I finally go, light switch on a wall, the transistor is like that, switch it on, you get current, you switch it off, you don't. That is the basic principle of where I was starting. Now today, people would go, kind of roll their eyes and then say, okay, whatever. Now people are saying, what are you doing to fix the problem? Right, so I think it's very much a change in terms of how people view the role of semiconductors. And I think there's a period of time, particularly for people who work in analog. Recently, I was talking to somebody who did a PhD in Ireland at the same time as me in UCC, and he quoted, and at that time within Ireland, I mean, there's a small semiconductor industry within Ireland. Analog devices was one of the industry that hired a lot from my university. And one of the things he quoted to me was the average age in terms of within the analog industry. And it had progressed, but one of the nice things about the analog right now in terms of more than more, and people are talking about sensors, it's actually getting a whole lot of people back interested in the analog as well as the digital. So if anyone thinks that technology and semiconductors aren't going to be important in the world from here on in, I say think again, because the reality is COVID, the sad situation with COVID, the silver lining of it was into the semi-industry. It really accelerated the rate of digitization within the world. And I think we're only starting the first steps of seeing, again, the next level of what's possible. I can't go forward without talking about Moore's Law. Now, some people will say Moore's Law is dead. My definition, my next question to them, so is innovation dead? And nobody has yet admitted to me that innovation is dead, right? Because innovation is the foundation of Moore's Law in terms of us continuing the progression within the development of the semiconductor, the transistor and process themselves, the design, the architecture. So by no means are we done with in terms of where we can move forward. Moore's Law is all about, before it was all about scaling. Now, as we find new ways of getting around that, so for those who are familiar with EUV, the move to EUV was a lot slower than was originally predicted. But the reality is we found ways to innovate to get around that until that technology was ready. So when there is a focus among all of us within the industry, we can move mountains or we can move tiny little atoms. The other thing is, I often say at work, my day is half an atom away from being a great day or a bad day. But the reality is we're working down at that level and that scale and that level of innovation. So for those of you who have an interest in terms of the semi industry, I'll say come on in, because the reality is it takes a huge diversity of people, of skill, of capability to make this happen. Within my organization, within TD, I have many PhD students. I have some students who come with us in terms of internships, with many people who have graduated from across the world, some here from Berkeley. I have PhDs in all disciplines. I have people who don't have PhDs, but they're also bringing a whole set of skills. So I believe the diversity of skill coming in, the diversity of thought coming in, the diversity of perspectives coming in is absolutely critical for us to continue to maintain the innovation going forward and actually deliver on what Gordon Moore said basically many, many years ago in terms of that we're about every 2 years we're able to pack about twice the number of transistors into a given product. Between the scaling and technology process and packaging, I believe we have given ourselves a goal of getting to about 1 trillion transistors by the end of the decade. I mean, will it be precisely 1 trillion? Okay, it might be 1 trillion and one, it might be one less than it, who knows? But the key point is that we're on that trajectory of innovation. So one of the things what excites me about working at Intel, well, I could say my paycheck, but I mean, there's a point at where just the paycheck gets old. It's not the paycheck, right? It's all about, I truly believe we're creating world-changing technologies that improves the lives of every person on Earth. That's what motivates me to do this job every day. That's what motivates me in terms of the work my team does. How do we make tomorrow better than today? How do we move the technology forward so that we can actually enable that change? And I call ourselves stewards of Moore's Law. Gordon Moore was one of the founders of Intel. So as I lead technology development, I feel a responsibility to be a key steward of Moore's Law because to me it's about innovation. And I have many of the best and brightest engineers in the world in my team. My job is to enable them to go forth and innovate and deliver and not get in their way. Another, Andy Grove, he did his PhD here in 1963, and he was Intel employee number 4. So we have strong connections over many, many years with Berkeley. And how many, I shouldn't ask how many here were born in 1963. I wasn't quite, but close. Right, so it's over many, many years, right? So, and some of you may say, well, that's so last century, Anne. But the reality is the relationship with Berkeley and Intel has been going on for that period of time. And people who have studied from here and around the world, if you think of the work that Gordon Moore did, Gordon, Andy, and Rob Noyes in terms of setting up Intel, think of the impact and the change it has made in the world over the last 50 years. is phenomenal. Think about what the change can become from the next 50 years from what people in this room will innovate. And sometimes it may look really, really small and insignificant at a point in time. But out over time, one, I will say, relatively simple invention can make a huge difference within the world. So a big part of what is also important to me is growing the future of the industry and growing the future of the industry. Yes, there's a piece about developing all the materials, all the equipment, etc. But you know what? Materials and equipment are just materials and equipment without people. And the key pieces in terms of growing our industry for the future is growing the skills from colleges, growing the skills from universities, whether you come with a master's, PhD, or a graduate, or even within in the factories to run, we also have many technicians. So there's an entire gamut of skills that's required. Growing the skills is absolutely critical in terms of enabling the industry going forward. And the one thing I can guarantee for anyone who's working in the industry and who's working on the research, no day is ever boring. You're working with innovation of new materials. You can be new compute types, new design types. And I rarely find my days boring is the best way of putting it. And any time over the last 20 years, this is year 27 with Intel. And I think there was probably about 3 days in the 27 that I could honestly say, I'm bored, I should think about doing something else. And then unfortunately I had said it to my boss and then I was doing something else. Now to finish, and I'm going to finish up on this, right? And so many of you are heading towards your graduation. Many are heading towards making choices. I mean, some people make choices by not making a choice. Okay, that is a choice in its own right. Right, I would all advocate for you to think about what you do really well. Think about what really gives you your passion. It's a long time between graduating and the time you retire. You better enjoy your job between here and there. And I would say think about what gives you every day, what motivates you. If only thing that motivates you going to work is a paycheck, again, it's a very long time between here and retirement. So I would say you have choices coming. I'm going to advocate for the semi-industry. Come on in, there's lots of opportunity for you. Now, but even if you don't, my ask is go and choose what you're good at, go and choose what you enjoy. And thereby, if you really enjoy doing something, you'll become really good at it. If you're really good at it, you'll do things really well. If you do things really well, you get more success, and it gives you a really successful career. So on that note, I'm going to stop.
Right, so we're going to set up some chairs here. I'm just curious, how many people here actually have heard about the CHIPS and Science Act of 2022? Maybe it has something to do with the great turnout here. Maybe that would be a great first question for me to ask Anne, just to get us started. And then we're going to pass the microphone around for people to ask questions. So Anne, what's so great about this CHIPS and Science Act? Like, what impact do you think it will make in this country?
Well, first of all, I think it's historic legislation here in the United States, because it is the US government recognizing that for the industry to be flourishing industry here in the US, it needs to balance and address the imbalance of funding that the industry has got overall compared to other countries. I'll break it down into two pieces. There's about 28 billion allocated to manufacturing, and there's about 11 billion allocated to basically research and development and startups. For the manufacturing, I think once it comes and once it gets, I'm going to say, fairly distributed, in the ideal case is that it actually grows the manufacturing footprint here within the United States, so that the United States has, again, grown its balance of supply of semiconductors from the US, it drops significantly and starts to grow that back. If I talk closer to home, the one that's probably of most interest to many of you here is the research work. I think there's the money that comes from that is First of all, I'm going to say I hope it actually ends up so it moves the needle. It moves the needle for the industry as a whole from a research and development. I think a key piece of it is workforce development. So in terms of workforce development is universities. I think while I don't work in a university or haven't been in a university here in the US, I can see universities worldwide are constantly in the need of funding so that universities can maintain its labs to be cutting edge. I think there's a key piece of it that needs to go into that. So I would say workforce development. Then within industry, how do we continue to grow the research and development at the cutting edge so that we can continue to get the IP into manufacturing so that US overall will be at the leading edge in manufacturing.
That's great. That was a lot. Okay.
Sorry.
So for people who might not be experts in the field, how much does it cost to build a leading edge semiconductor manufacturing facility today?
Well, first of all, it's a bit like building a house. It depends on the size, right?
Yes.
And I start from there, and I say that because many people compare fabs and based on their costs, and they don't compare the size. But typically, a factory these days is about 2 miles, which would be roughly close on 500,000 square feet close, I say that. The buildings itself can be about 10 billion. And then the capital for leading edge can be about 18 billion. So the bottom line is you're talking about a hell of a lot of money by the time you're finished getting it up and running. So you're talking about the best part of about, based on size, can be anywhere between 20 to 30 billion, depending on the size of what you're doing and the node you're on. So it's a really, really big investment for companies to do. Now, if you're on older nodes, it's less. But for the leading nodes, that's kind of the range in terms of the costs.
Yeah, pretty sophisticated equipment. And you talked about, well, first of all, I want to express appreciation to Intel for really leading the industry and investing in workforce development. Intel is one of the biggest sponsors of research and education programs here at Berkeley and at other universities. So maybe can I ask you about workforce development? You mentioned a diversity of people, like from different disciplines and so on and so forth. How about the ability? Because here at Berkeley, we are trying to educate our students not only to be outstanding in technical knowledge and skills, but to be able to work effectively with others. So what about how important is the ability to work with a diversity of people?
I think it is important. I mean, one of the things I often remind people, no person is an island. You might be an island if you can work in a lab somewhere on your own and produce results on your own. But that's a very rare case. No person is an island. So the ability to work with others is important. Now, people have various ability in that, but I mean, the ability, if people are in team sports, typically they're relatively good because they've learned how to work as a team. So I will encourage everyone as you go work out, understand how you work at a personal level, right? And then work out how you work as a team because it is really important. I go back to talking about the diversity of skills, the diversity of people. I mean, a mechanical engineer on their own will not deliver in the fab, will not deliver a process. Process engineer on their own will not deliver. It's a chemical engineer on their own won't deliver. An electrical engineer on their own won't deliver. But when you put the sum of all of those on material science together, then you get the ability to deliver. And you won't be able to do that unless people are able to work well together as teams.
Yeah, and you touched upon, I mean, there's a major theme in your talk, innovation. So it's all the more important. If you want to come up with the best ideas, the most creative solutions to solve the technical challenges to reach 1 trillion transistors on a chip, you want to have a great diversity and bring out the best ideas from a diversity of people.
Correct, absolutely. Yeah. And the other thing is quite often, I always say in the industry, there's no such thing as a bad idea. It's often a question of timing, right? And quite often one person will have an idea and somebody else will look at it and it will trigger another thought for them and somebody else will look at it again and get another thought. It's that greater thought process that often brings the greatest innovation and inventions.
Yep. So we'd like to attract the best and brightest to the field of semiconductors, right? So maybe you can tell us what is the most rewarding part of your job, and how does the engineering educational experience prepare you for that?
I think the most rewarding piece of my job, and actually that is either today and what I'm doing today or even when I was in manufacturing, is enabling getting really good results through people. I like working with people, I like coaching people, I like haranguing people if needs be, right? But I like the ability to work together as a team to get the result. The result without having the good teamwork doesn't do it for me. Having great teamwork and just be cohesively dysfunctional and happy doesn't do it for me. You have to get both together. So that really motivates me, right? I think back when the first time I became a manager, it was back in my research world. One of the things I had to learn was, I'll admit, I basically have an edge. When I say I have an edge, I can have a sharp tongue, right? So one of the things is I needed to learn was to soften my approach with people, and that was one of my first learnings as a manager. How do I work with people without stepping on people? How do I work with people so that you motivate people to get the result, rather than actually somebody feeling this high after an interaction? I remember one particular morning, this was when I was working in Fab in Cork, and let me just say there was something processing, and something had happened a lot overnight, and I was less than happy. And I said what I thought, right, without filter. And my boss took me outside later and said, you know what, Anne, if I was the person who was doing that, I wouldn't be very happy. So it was a key teachable point of view for me, and I still keep it in my head in terms of how do I bring people without actually stepping on people.
Yeah, so inspiring and motivating people is a good, important trait for an engineering leader like yourself. What are other skills or traits of successful engineering leaders?
Successfully, I think be clarity of thought in terms of what you need to deliver is absolutely critical as well. And I say clarity of thought, right, with that becomes logical thought. Quite often people get very focused on what they deliver, not on when they need to deliver it. And I think every project, it doesn't matter whether you're in research or whether you're in industry, there's a when, right? So the clarity of thought and connecting it to a timeline is actually very important, because if you know what you need to do, right, and then actually are able to break that down, you'll have a good idea, can you do it in the timeline you've signed up for, or do you need to do something different? And I think being clear on what you need to deliver and then effectively delivering it is absolutely key for basically leaders within our industry, even within research.
Yeah, so innovating new solutions, but with real constraints.
With real pragmatism.
Time.
There's a pragmatism.
Cost.
Yes,
yeah.
Exactly, and pragmatism.
Okay, so I'll ask one more question before we open it up to our audience. What advice would you give to today's students who might be among the very few or the first in their chosen professions? You mentioned that you're the first woman who got a doctorate, or earned a doctorate in electrical engineering from UCC. Like, what advice do you have for people who are the first?
One of the things that I find in this life, a lot of people will find all the reasons why you can't do something. And it's okay, people can give you the reasons, but I would advise you to spend the time on what can I do, right? Look for the possibilities. Now you have to be pragmatic. I can't sing a note, and if I decided I wanted to be an opera singer, it ain't going to happen, right? So you have to be pragmatic as well, right? But I think look at what your skills are. Reflect in terms of what you're good at. Reflect in terms of we all have areas we need to develop. And if you think you have key skill gaps that you need to develop, work on developing them. But I think the key thing is you also have to have self-belief, right? And again, a pragmatic self-belief, because if you constantly doubt yourself, guess what? Then you just feed into everybody else doubting you. So I would say be pragmatic, look for the possibilities. You know what? Nothing ventured, nothing gained. If you don't try something, you'll never lose. One of the things is part of the reason I got to this job over the years is there were times when I took jobs which other parts of my peers, as I worked my way up in Intel, people thought they were too risky, right? And they thought they were too risky because they thought, oh, I'll never be successful at that. Now, a few times I got roles because the music stopped and I wasn't on the chair, right? But that's okay, right? But they were challenging jobs. But I also learned from them. And I think some of my biggest learning moments was when I was doing some of those roles, because you stretch yourself. The other thing is, one of my key learnings out of that was work well with other people. I call it the emotional bank account. Deposit into it, and you see when you're in a corner and stuck, people will help you. There was one role that I took, right, and there was about 6 months into it, I thought, oh my goodness, maybe I won't come out of this one, right? And I actually went out and I asked for help, and it was quite amazing how many people at all the factories that I had worked with over the years and helped all showed up. And I mean, then we turned it around and we got there. So help people, right? Believe in yourself, help people, be pragmatic, look for the possibilities. And depending on your personality type, not everybody is good with risk. I recognize that. I'm fine with risk. I mean, that's okay. Not everybody is. Take on the risk that's appropriate for you, that you're comfortable with as a person.
Great advice. Thank you. All right, we have the first question here. Yes, please introduce yourself and maybe introduce your major and your year as well.
Hi, so my name is Sarah Mithabedin. I'm a junior studying bioengineering. Thank you again for this. It's very inspirational, the advice that you just gave. But I had a question about just like semiconductor technology, and I was wondering, is there any semiconductor technology that is up and coming or recent innovations that you think will significantly advance the industry as a whole in the future?
It's a very interesting question, right? I think one of the things is, and I won't speak about internal to Intel work, but I'll speak about external published. One of the things is there's a lot of talk about slowing down in Moore's Law, and there's a lot of talk in terms of how do we continue to maintain scaling. I think the next place in terms of where we go that can truly influence that is stacking within the technology, PNN stacking. Now, right now it's out there as published papers. That is one aspect for it. 2D materials coming, I think, are also really, really big, right? In terms of potentially big, right? As I say, I'm watching Suja's face, right? Whether she agrees or not, right? But the reality is, I think there is unique innovations that, when they all come together, will actually help propel us forward. Some innovations take a lot longer than others, right? So EUV, I'll go back to EUV again because EUV has been so critical. The industry had aspired that it would be ready in 2007. It was about 2017 when it came. So the question, and one of the questions that Martin van den Brink, who is the Chief Technology Officer in ASML, and I were having very recently, so what's beyond EUV? Is there something beyond EUV? There's High-NA, and then where do you go beyond that, right? So I think it's a lot of stuff I would say in the melting pot. And I mean, my hopes are quite high for the future.
Just in case there are people here who are not electrical engineers, so EUV means extreme ultraviolet light. It's about 13 nanometer wavelength used to define the patterns for each layer of the integrated circuit. ASML is the leading lithography tool manufacturer who enables the industry to print such small features.
Thank you, Suja. I'll remember. I'll do better.
No problem.
All right.
Yes, please.
I'm Neil Murray. I'm an integration engineer who works in the Nano Lab here. I have a question about developing R&D lines for new technology in these big fabs. Do you see having a dedicated R&D line as a more beneficial pathway, or having something that's fully integrated with your manufacturing line, but with the risk of contamination or having to worry about, running the two processes together?
It's a very good question, and I'll explain how we do it, and I explain. So for our components research, we have components research, which does the advanced research, which is basically, it might anywhere between the science experiment to something that may ultimately get into development in that regime. What we do is, for the steps that are common with the rest of the technology and no change, we allow those on the other equipment that runs. Some of it runs the development and some of it runs manufacturing. But for the unique materials, we actually keep that very separate on its own equipment. There are many reasons for doing it, right? There's contamination to the silicon, but you also have to take into account the environmental. How do you deal with the waste systems? How do you deal with everything that goes with it? So until it's proven that it is not going to impact the rest of the technology, we keep it isolated to those steps. But then I'll go back to talking about the technology development with manufacturing. In our technology development line, we have some equipment which is dedicated to that, but we also, in my factory, we run a large amount of manufacturing. The benefit of running TD on some of the same equipment is you get the stability of the process flow, you get the stability of the equipment. I know from my own days of when I worked in research, and I know from some projects that I've run with some research institutes, I leave it all nameless, right? But the variation in the equipment, it's not set up to be stable enough, and thereby can really mess up the experiments unless you have a stable baseline.
Wonderful. The next question.
Hello, Dr. Keller. I'm Nagar. I'm a freshman in bioengineering, and I was wondering, in your introduction, you mentioned that you first wanted to be a vet and then compromised with your mother to be a doctor, and then you made the switch to electrical engineering. I was wondering how you made that switch, and also your general thoughts on how interconnected the different STEM majors are.
Well, first of all, thank you. I never started learning medicine, right, because that was my mother's choice, and I said she had one part of the argument, I was going to win the other part, right? So one of the things is I actually sat down and actually I went through what I enjoyed doing, and I enjoyed chemistry, I enjoyed biology, I enjoyed physics, I enjoyed mathematics, and based on that I decided I would look at that field in my local university, and electrical engineering honestly was the toughest to get into, so I said, okay, I want that. And by the way, I am, it aligned with my interests. The other thing at that time when I was going to college, I mean, Ireland is not a large country, and I also had to, I know this is going to sound ironic, I actually had decided I want to live and work in Ireland, and I was looking at where were the jobs in Ireland, right? So engineering was one of the jobs, one of the roles which also gave me the opportunity to work and live in Ireland. But the best made plans change, and here I am.
Next question.
Hi, this is Jason. I'm a PhD student with Professor Sabi Sullivan's group. My question will be, innovation and looking for the next generation of technology for semiconductor. Usually, it's a very long period. I think there's kind of a two-part question. How do you think, is there a better way to improve or accelerate that process? Is that actually something we want to do? Or is it the slow, our usual cycles is what we actually want to, could be maintaining a good reliability or process control? And how would you think university can help in this aspect?
Well, I'm going to put on the purity of, ultimately, I mean, we're in a business where our work turns into a product and we want to sell the product. So the purity of the answer in that is the faster we can do that, the better. That's the purity of that side. But I think we also need to give enough time to incubate the technology so it's ready. Sometimes, I mean, you can put in a technology, if it's not ready, it creates significant manufacturing problems and you're not going to get the benefit from it. And I think it very much depends on the innovation that's ongoing. Some of it will give you enough robust data fast enough that shows you can move faster on it. Some of it, and I go back to the EUV area, basically the lithography again, that was 30 plus years in the making. And I think sometimes one of the challenges that becomes in the industry is how do companies have enough patience to wait for it? And I think that's a key part of where universities, not only can they basically test the leading edge, but also have the patience to work with stuff. Because today extreme UV lithography is the reason why we can continue to progress. But if the industry, and it came very close about 10 years ago, the industry almost ran out of patience with it. So I think it becomes, universities can absolutely help us in the industry to not run out of patients.
To this point, though, maybe going back to the U.S. Science, the CHIPS and Science Act, there is funding to actually try to accelerate this process of translating innovations from university labs to manufacturing fabs.
Correct. And then that becomes an idea, and when I say universities can help on it, when it's proven to be ready, I mean, in terms of a set of criteria, if we can get it out into pilot lines faster through the NSTC, that will also help.
So NSTC is a National Semiconductor Technology Center, which is going to be funded because of the bill that just passed.
Yeah, partly too.
Hello, my name is Ishida. I'm a freshman in the electrical engineering and computer science major, so go EE. But my question was that in your work, when you're looking at Moore's Law, essentially you're trying to do what's like not possible yet, like you're kind of making a completely new thing possible. So I was wondering, how do you kind of get into that mindset of trying to look at something that everybody thinks is impossible and actually create it? Because it seems a little overwhelming.
First of all, you need to believe. And I honestly, and I say that for many of my integrators and folks who are working today, they have to, first of all, you need to have the fundamentals of science and physics and all of that. And you also need to have, I would say, some idea within those that it is possible. But I mean, within that, you also need to have a good dose of belief in that you can make it possible. Because quite often when you're doing innovation, the innovation you start out with might not be the innovation you finish with, right? Because you learn a whole bunch of more stuff along the way that you end up changing direction, and your end result becomes significantly better and more usable than your start. I mean, it's like all research. I mean, I view all research, you have to believe you're learning something new, you're looking something new, you're going to make something new. And I think there's probably a lot of belief in this room, right? Because if there wasn't, you wouldn't be part of what you're doing today, right? And who in research wants to do the exact same as what somebody else has done before? I think the very essence of a PhD is you're publishing something new, or it was when I was doing it, and I doubt if it's changed, right?
Still the same.
You're publishing something new, so thereby you have to believe as you start your PhD, you're going to be able to do something new.
All right. Hi. So I'm Carla. I'm a first-year PhD student in mechanical engineering, and I'm also interning at Intel right now.
Excellent. I hope it's going well for you.
Yeah, it's great. So you worked in manufacturing operations before moving to technology development, and I'm curious what your day-to-day is, or how your day-to-day is different working in each of those, and why you made the switch.
Well, first of all, my boss asked me to make the switch. It's probably the first honest, is the honest answer in terms of why I made the switch. But I said earlier when I was talking, a lot of what I learned when I was doing my PhD is very relevant for me today. I mean, in my day-to-day difference when I was in manufacturing, it was all about how do we get the output, how do we get the supply, how do we get the chips, how do we get it all there so that our customers had parts. Today, part of my factory does run manufacturing, but from an Intel level, I don't. And my peer, Kayvon Esverjani, does that now, my job before, so I'm not worried at the same level as how we do all of that from a daily perspective. My thought process is around, and my work is with my team in terms of anywhere from the most advanced research, have we the projects in place and are the teams working so that we can either internal to ourselves or working with universities and research centres worldwide that funnel is wide enough. Closer to home as we're working on Intel 4, that'll be going into, I'm basically ramping the end of this year for products out next year, making sure we're marching down on our committed goals and hitting all of that. So it's very much around are we delivering against our development? Now, obviously, I spent 23 years working in manufacturing, and it was over 23 years since I worked in research. So, I mean, the foundations I did on that was absolutely critical. A lot of my time was on device physics at that point in time, the transistor. And I'm just really glad I did, because at least now I'm able to follow in terms of my team, in terms of, and able to ask the questions or smell BS, right? And that's part of being in the role, is just smell when stuff isn't quite right. Because I'm not doing the development day in, day out, but my job is to watch for, we're going in the right direction. How do I enable my team to deliver on it?
Wonderful.
Hi, my name is Judd, studying chemical engineering. I'm a senior, and I was wondering what your opinion on the transition to 450 millimeter wafers was, and what direction you think that Intel is going in. I understand that the transition to 300 millimeters was rather difficult, so I was wondering your opinion, given your stance on innovation.
The transition in the size of the wafers has always been about cost, right? The 200 millimeter to 300 millimeter was driven by cost. It wasn't driven by, I would say, technology innovation. If I go back over a decade, there was an active work in the industry, and how do we go to 450? It's very expensive for the industry overall to transition from a size of wafer. And I think my simplest way of putting it was somewhere around by about 2015, everybody was staring at it, but nobody was willing to write the check. Right, and thereby it was decided as a whole that the industry would stop. Could it come back in the future? Maybe, right? Would I love to have it today? Yes. But I mean, the reality is it's a very expensive move for the industry as a whole, and the industry as a whole would need to move. So I think it's not in our immediate horizon. Maybe in a decade's time, everyone will look at it again with a fresh set of eyes. But it's the cost of moving becomes one of the biggest barriers. And for many of the suppliers, equipment or even silicon suppliers that had done quite a lot of work and research on 450, it was very expensive on them. And when we stopped, it was quite impactful on within the supply chain. So I know there's not a lot of the equipment or material suppliers would be automatically putting up their hand and saying, let's do it.
We have a question back here.
Yeah, hi, so my name is Michael. I'm a PhD student in electrical engineering. So earlier you touched on the point of transitioning research from university to industry. So yeah, how do you determine when a project is ready to go into main manufacturing? We have, there's a lot of, I would say, criteria which we apply in terms of whether a project is ready. There's different phases. There is it ready to go from research to actually ready to go into like the early phase of a prototype, to the development, to ultimately manufacturing. And at each phase of those, we have a certain set of criteria. I mean, at the base level, if you're talking, say, about a material, it has to have a set of electrical characteristics. It needs to have reliability, and it needs to be able to be manufactured or basically made repeatably. So all of those, then as you go through each step, we have a different set of criteria. And it needs to be repeatable, it needs to have good reliability, high reliability, needs to be of high quality, and it also needs, whatever the nature of it is, needs to be so that you can actually have equipment that makes it, and also that you're able to maintain that equipment. I mean, sometimes I've seen great ideas, but it's a nightmare to keep the equipment running. And then it becomes, does it make sense or not? So there's many checks and balances, right, to go from point A to being manufacturable.
Back here.
Hi, I'm Delania. I'm a junior and I study electrical engineering and computer science. And I'm hoping to do research in electrical engineering in the future, so this was really interesting. Mm-hmm. But my question was about the Aurora supercomputing system that Intel had planned to release a while back, and now I think they're planning to release it later this year. My question is what needs to happen in the process of innovation for a team to be able to pull that kind of thing off by a deadline, or in other words, what didn't happen in 2021 that caused the delay. I'm just curious, but thank you.
I'll break it down into pieces, and our internal name for that particular product is called Ponte Vecchio. And believe me, Ponte Vecchio is very near and dear to my heart. Every Friday morning I get an update on it, and to get the product itself is quite complex. I mean, it is one of the most advanced set of packages we've ever done. I think it's probably the most advanced package that is in the world, right? It is 47 pieces of active silicon packaged together into one product. There's over 100 pieces of silicon, but some of the pieces of silicon are not active, they're passive, basically so that we can do the packaging. If I step back over time, originally, the original product was tied to our original, what we were calling 7nm timeline at that point in time. When that pushed out, that actually led to a delay in the product overall. I think I would say it has been a feat of engineering to get done what we have done with Ponte Vecchio itself. And I would say it's been a series of backflips in manufacturing to take what was done. Your question earlier around how you go from your innovation to actually make it manufacturable. A lot of the last year is in terms of, okay, we've proven we can do this, now how do we make all of this manufacturable, has been a key part of that activity. I'm very happy to say all the factories certified is our name in terms of this, is they're good to go in manufacturing. They're all done, so I had a major sigh of relief when we achieved that.
Okay, I think we only have time for one more question, and we're going to do it right back here. And while I have the microphone and everyone's attention, the Dean very graciously said that everyone got a lunch. As you can tell, we've had a stellar turnout. We also have many people out in the atrium watching as well. So we're going to try and prioritize people that got here early and got a seat and ask you to go out these doors, and we're going to accommodate as many people, the doors here to my right, your left, my right, and we're going to accommodate as many people as we can with lunch, and we're going to thank you in advance for your graciousness if we unfortunately can't serve everyone. So here's the last question.
Thank you.
Hello, my name's Donnie. I'm a fifth-year chemistry PhD. I was wondering, you talked about stewarding Moore's Law, and you also talked about pragmatism, so I'm wondering, pragmatically, when does Moore's Law end? Is it 1 trillion? Is it 1,000 trillions? And when do you focus instead on architectures or materials or even software to make those advances rather than focusing on number of devices on a chip?
Well, I think the number of devices on a chip is a way of measuring are we progressing in Moore's Law. But I think all of those innovations needs to be happening today anyways, right? Because as we progress, we'll draw from many disciplines to keep progressing our ability to be able to deliver more, faster, better, less power, more efficient in terms of the products that we deliver. And I go back to my point in terms of innovation. Innovation is needed in all of those, and it's the collective piece of that that will continue us to be able to keep marching forward in the industry. And I can stay a few minutes. I know Dean Liu has to get to a meeting, but I can stay and chat afterwards as well for a little while if you want, if you didn't get your question asked.
Thank you so much, Anne, for spending your time with us today. Thank you.
Oh, wow. Thank you very much.
Small token of our appreciation. And thank you all for coming. All right, go Bears.